One of our solar system's greatest wonders is quietly fading from view. For centuries, Jupiter's Great Red Spot has dominated the face of the gas giant, a storm so vast it could swallow our entire planet. But telescopes now reveal this ancient tempest is shrinking, and no one is entirely sure why. By the end of this exploration, you will understand the forces that may be dismantling a giant and what its fate reveals about the hidden workings of alien worlds. We will peer into the storm's deep roots with an orbiting spacecraft and untangle whether this is a natural cycle or an irreversible end. What does the disappearance of a cosmic landmark truly mean for us? The sheer scale of this phenomenon is almost impossible to grasp from a distance. Jupiter's Great Red Spot is not a cloud or a simple weather pattern. It is a persistent, high-pressure anticyclonic storm, a colossal vortex of churning gases rooted deep in the planet's atmosphere. Think of it as a hurricane, but one that operates on a completely alien set of rules. For perspective, at its historical peak, this swirling oval was so wide you could have lined up 3 planet Earth side by side, and they would have fit neatly within its borders. Even today, as it shrinks, it remains a behemoth capable of engulfing our entire world. Its most striking feature is, of course, its color, a deep, rusty red that stands in stark contrast to the creamy whites and tans of Jupiter's swirling cloud bands. This color is believed to come from chemical compounds, perhaps sulfur or phosphorus, being dredged up from the planet's hidden depths by the storm's powerful currents and cooked by ultraviolet light from the sun. We have watched this spot for a very long time. Continuous, confirmed observations date back to 1830, but there are intriguing sketches from astronomers like Giovanni Cassini in the 1660s that may depict the same storm. This means the Great Red Spot has been spinning, a landmark in the sky, for at least 2 centuries and possibly for over 350 years. It has witnessed the entirety of modern astronomy, from the crude telescopes of Cassini's era to the breathtaking, detailed composites sent back by the Juno spacecraft. Our view of the spot has transformed from a curious smudge into a map of a raging, ancient giant. Yet, through all that time, one question has persisted. What keeps it alive? And now, a new, more urgent one has emerged. Why is it fading? This storm was churning before the United States was even a nation. While its continuous record is anchored in the 19th century, its story begins in the flickering candlelight of observatories over 3 centuries ago. In 1664, the English scientist Robert Hooke noted a spot on the disk of Jupiter. A year later, the Italian-French astronomer Giovanni Cassini began a meticulous, decades-long study of the same feature, sketching its movements and proving it was part of the planet itself, not a moon passing by. For nearly 50 years, until 1713, Cassini and his colleagues tracked this permanent mark. Then, mysteriously, the records fell silent for over a century. Did the storm fade from view, or did astronomers simply lose the thread? When it was definitively rediscovered in the 1830s, it was given the name we know today, the Great Red Spot, and it has never left our sight since. This makes it the longest continuously observed storm in the entire solar system, a scientific treasure that has witnessed the evolution of our own understanding. For generations of astronomers working with ground-based telescopes, this persistent, swirling oval was the key to unlocking Jupiter's secrets. By timing its rotations and mapping its slow drift relative to the planet's cloud bands, they could calculate wind speeds and atmospheric currents. They deduced the basic structure of Jupiter's weather long before any spacecraft could get a closer look. It became, and remains, the ultimate classroom example of planetary meteorology. Every student who peers through a telescope at that orange speck is connecting with a legacy of observation that stretches back to the dawn of modern science. It is more than a storm, it is a symbol of cosmic endurance and a reminder of how much we have yet to learn. Yet this enduring symbol is powered by forces utterly alien to our own world. To understand why the Great Red Spot is shrinking, we must first grasp the strange mechanics that allow it to exist at all. Jupiter is a world without a surface, a gas giant composed almost entirely of hydrogen and helium. There is no continental crust to break up a storm, no mountain range to disrupt its flow. Instead, the planet transitions gradually from a gaseous outer atmosphere to an ocean of liquid metallic hydrogen deep within its core. This lack of a solid ground is the first key to the storm's longevity. A hurricane on Earth rages itself out when it moves over land, its energy source cut off. But the Great Red Spot spins over a bottomless abyss with nothing below to slow it down except the churning fluids of Jupiter itself. So what keeps this giant vortex spinning? The storm is a colossal high-pressure system, an atmospheric mountain. Within its boundaries, gases are forced upward. As they rise, they expand and cool, forming the distinctive, bright red clouds we see at the very top. These cooled gases then spiral outward from the center, sink back down along the storm's edges, and are warmed once more, creating a continuous, stable cycle of circulation. It is a self-perpetuating engine, but an engine needs fuel. On Earth, our storms are powered by the sun's heat, which evaporates ocean water and creates the energy for hurricanes. Jupiter's primary power source is different. It radiates more than twice the heat it receives from the sun, a leftover warmth from the planet's violent formation over 4.5 billion years ago, combined with the slow gravitational compression of its immense atmosphere. This internal heat drives the convection, the rising and falling of gases that stirs the entire planet. The other crucial ingredient is Jupiter's dizzying speed. The planet completes a full rotation in just under 10 hours. This rapid spin stretches weather patterns into the long, parallel bands we see and provides the Coriolis force, the same effect that makes hurricanes spin on Earth, but on a vastly amplified scale. This force is what gives the Great Red Spot its specific rotation. In Jupiter's southern hemisphere, high-pressure systems like the spot spin in an anticyclonic direction, which is counterclockwise. Picture a massive wheel turning slowly against the flow of the jet streams that flank it. It is this combination, a deep well of internal heat and a planet spinning so fast it bulges at the equator, that has fed this storm for centuries. It is not merely a cloud, it is a dynamic feature rooted in the very fundamentals of how Jupiter works, a manifestation of the planet's ferocious energy written across its face. But a landmark that has endured for centuries does not simply vanish without notice. The evidence of its decline is etched into 1.5 centuries of photographic records, a slow fade captured in snapshots across time. In the late 1800s, when astronomers made the first reliable measurements, the Great Red Spot was a sprawling giant. Estimates placed its width at a staggering 40,000 kilometers. You could have flown a commercial airliner around its perimeter for over 2 months without stopping. By the time the twin Voyager spacecraft raced past Jupiter in 1979, humanity got its first close-up look. The images were breathtaking, revealing a storm of swirling, complex textures, but they also delivered a surprise. The spot had contracted. It now measured about 23,000 kilometers across. The process has only accelerated in the decades since. The watchful eye of the Hubble Space Telescope and powerful ground-based observatories now measure it at roughly 16,000 kilometers wide. Less than half the size it was when our great-great-grandparents looked up at the sky. This is not a subtle change, it is a profound transformation. The storm is not just getting smaller, its very shape is evolving. For most of its observed history, the spot was distinctly oval, like a massive egg set sideways in Jupiter's southern hemisphere. Now it is undergoing what scientists call ovalization. It is becoming more circular, its once elongated form tightening into a denser, more compact vortex. You can witness this yourself in time-lapse animations compiled from decades of images. Watch as the iconic red oval, once so vast it dominated planetary portraits, steadily shrinks and rounds out before your eyes. The change is both gradual and undeniable. But is it a smooth, constant decline or something more erratic? The data suggests the latter. The shrinkage appears to happen in fits and starts. There are periods of relative stability where the storm holds its ground for years, followed by episodes of rapid contraction where it sheds thousands of kilometers in width in just a few Earth years. This uneven pace hints that the forces acting upon it are not simple erosion, but a complex interplay of deeper atmospheric battles we are only beginning to map. The storm's slow fade points to a hidden battle in the skies of Jupiter. The most compelling suspect in this cosmic mystery lies not within the great red spot itself, but in the powerful rivers of wind that surround it. Jupiter's atmosphere is a tapestry of jet streams, bands of wind racing east or west at speeds that can exceed 600 kilometers per hour. The great red spot sits pinned between two of these ferocious flows, a colossal, spinning boulder in a raging atmospheric river. For centuries, the dynamics were stable. The storm acted as a solid obstacle, deflecting the jets around its flanks in a smooth, predictable pattern. This interaction actually helped maintain the spot's structure, feeding energy into its rotation in a delicate balance. But what if that balance has shifted? Recent observations and sophisticated computer simulations suggest the jet streams themselves may be changing. If these flanking winds weaken or subtly alter their course, the effect on the vortex would be profound. Instead of flowing smoothly around the stone, the currents might begin to scrape against it. Imagine a log jam in a river. If the water level drops and the current slows, the logs might hold their position. But if the water surges with new force or changes direction, it begins to tear pieces from the edges, wearing the jam down bit by bit. This is the process of atmospheric erosion. The simulations are clear. They show how the shear forces, the difference in speed between the storm's edge and the jet stream, can literally strip material away. Clouds and gases that once belonged to the vortex are sheared off and carried downstream, lost to the chaotic flow of Jupiter's broader weather systems. Each of these events, these moments of erosion, translates into a measured loss of width on our telescopes. The spot isn't simply evaporating, it is being actively dismantled by the changing currents of its home world. This theory turns the great red spot from a solitary wonder into a participant in a planet-wide atmospheric dance. Its fate intimately tied to rhythms we are only beginning to sense. Yet the great red spot does not fight this battle alone. Jupiter's southern hemisphere is a crowded sky, a turbulent sea dotted with swirling white ovals and smaller anticyclonic storms. These are not mere clouds, but powerful vortices in their own right, some as large as continents on Earth. For decades, astronomers have watched a slow-motion dance of giants as these storms drift, merge, and sometimes collide. The Great Red Spot, as the dominant feature, often acts like a gravitational bully, pulling smaller storms into its orbit and sometimes consuming them entirely. You might think a merger would make the spot stronger, adding mass and energy like a hurricane absorbing a smaller storm, and sometimes that appears to happen. Observations show the spot can temporarily intensify or change color after such an encounter. But these interactions are a double-edged sword. A violent merger is not a gentle feeding, it is a chaotic disruption. When a sizable vortex is drawn into the spot's outer circulation, it doesn't simply vanish. It slams into the storm's powerful flow, creating immense turbulence. Think of it as throwing a large, spinning rock into a well-ordered whirlpool. The resulting splash and churn can violently scramble the internal structure of the vortex, disrupting the smooth, rising and falling cycle of gases that keeps it stable. This internal trauma can force the spot to shed material, literally shaking loose huge plumes of its substance. The Hubble Space Telescope has captured this drama in stunning detail. In recent years, it has observed what scientists call flaking or blading events. In these sequences, you can see distinct blades of reddish material, hundreds of kilometers long, being torn from the main body of the Great Red Spot and shredded into the surrounding jet streams. These are not minor losses. Each flake represents a significant chunk of the storm's atmosphere being stripped away, carried off by the very winds it once defied. These dramatic images provide a direct visual link between the spot's interactions with other storms and its physical shrinkage. Every close encounter, every gravitational tug-of-war may come with a cost, weakening the giant's cohesion one chaotic merger at a time. So the question becomes, is the spot being weakened by a changing environment, or is it being picked apart by its own neighbors? But the most profound mystery may lie far beneath the visible clouds. The Great Red Spot is a surface phenomenon, a brilliant symptom of a much deeper illness or perhaps a changing heartbeat. Its ultimate power source is not the Sun, but the immense reservoir of heat trapped within Jupiter itself. This internal furnace, a relic of the planet's violent birth and sustained by the slow crush of gravity, drives the convection that stirs the entire atmosphere. Great plumes of warm gas rise from the depths, cool to form clouds, and sink back down in a planet-wide churn. The Great Red Spot sits atop one of these massive upwellings. It is essentially a chimney, a stable outlet for that deep-seated energy to escape. So what if the plumbing is changing? If the flow of that internal heat were to weaken beneath the storm or shift its location, the consequences would be direct and devastating. The storm would literally be starved. Without that consistent upwelling of warm gas from below to fuel its rising central column, the entire circulatory engine would begin to sputter. The vortex would lose its vigor, becoming more susceptible to the erosive forces of the jet streams. It would not just be worn down from the outside, it would be collapsing from within. This theory points to a cause far more fundamental than atmospheric squabbles. It suggests the spot's fate is tied to the slow, billion-year rhythms of the planet's own cooling and the chaotic dance of heat in its fluid interior. Proving this, however, is one of the greatest challenges in planetary science. We cannot see inside Jupiter. Our spacecraft can sense the heat radiating from the cloud tops, and the Juno mission has mapped the planet's gravity field in exquisite detail, revealing hints of its inner structure. But mapping the specific, real-time flow of heat from the metallic hydrogen core up through thousands of kilometers of turbulent fluid, and pinpointing how it surfaces in one specific location is currently beyond our reach. It is like trying to diagnose the health of a fireplace by only studying the pattern of smoke leaving the chimney without ever seeing the fire below. Artistic representations help us visualize the possibility. They show Jupiter's interior not as a smooth gradient, but as a seething ocean of convection, with colossal rising plumes and sinking sheets of material, like a pot of thick soup boiling on a cosmic stove. The Great Red Spot, in this view, is merely where one of these persistent boiling bubbles breaks the surface. If that bubble weakens or moves, the storm above it would have no choice but to fade. This connects the spot's shrinkage to the grandest questions of all. How does a gas giant distribute its heat over time? Is Jupiter's weather, which seems so chaotic, actually driven by orderly, deep-seated patterns that shift over centuries? The slow disappearance of our oldest celestial landmark might be the first visible sign of a change in Jupiter's deep, hidden metabolism, a faint surface signal of a planetary-scale transformation we are only just beginning to perceive. Its iconic red color holds a clue to the storm's changing health. That deep, rusted hue is not simply paint on the clouds, it is a chemical signature, a message from the hidden layers below. Scientists believe the color comes from compounds like ammonium hydrosulfide or complex organic molecules called tholins that are forged in the depths. The Great Red Spot acts like a powerful elevator. Its intense upwelling currents dredge these chemicals from warmer, lower layers of the atmosphere, where they are normally invisible, and lift them high into the cloud tops. There, they are exposed to the harsh ultraviolet radiation from the sun. This cosmic chemistry experiment, the cooking of deep gases by sunlight, is what produces the striking red pigments we see. The storm is not just a vortex of wind, it is a factory for color. This means the vibrancy of its red is directly tied to the strength of its internal engine. A vigorous, tall storm pulls up more material and creates a more intense color. A weakened one does not. So, as the spot shrinks and its dynamics alter, the vertical mixing that brings those colorful compounds to the surface may be slowing down or becoming less efficient. Think of a blender that starts to lose power. The ingredients at the bottom no longer get churned up to the top. The result would be a gradual fading, not just in size but in brilliance. And this is exactly what the historical record shows. Over the decades, the spot's color has not been constant. It has oscillated between a strong brick red and a much paler salmon pink, sometimes even appearing almost white to observers. These shifts often correlate with periods of observed shrinkage or changes in its structure. When the storm is robust and actively churning, it seems to flush itself with fresh color. When it is struggling, the color drains away. Modern telescopes allow us to see this chemistry in action, not with our eyes but through the lens of science. By observing Jupiter in specific wavelengths of light, astronomers can create false color and enhanced images that act like chemical maps. These images reveal stunning details, showing how the red material is concentrated in the storm's core and along its swirling rings, while the surrounding clouds are composed of different chemicals that appear white, tan, or blue. These maps prove the color is not superficial. It is a direct tracer of the storm's deepest, most powerful currents. So the fading of the red is more than an aesthetic change. It is a vital sign, a visible indicator that the spot's internal machinery is undergoing a profound transformation. The giant is not just getting smaller, it is growing pale. That fading red hue is a silent alarm, a call for our most powerful eyes to turn toward Jupiter. For the first time in history, we are not just watching the great red spot, we are giving it a full medical examination. The Hubble Space Telescope, orbiting high above our atmosphere, has become the storm's primary physician. Every year, as part of its Outer Planet Atmosphere's Legacy program, Hubble takes a detailed portrait of Jupiter. This is not a casual snapshot, it is a rigorous long-term health check. By comparing these annual images, scientists can track the spot's exact size, shape, and color with incredible precision, measuring its shrinkage down to the kilometer. Hubble's consistent gaze provides the critical timeline, the before and after pictures that prove the change is real and ongoing. But to understand the illness, you must look beneath the skin. That is the role of a different kind of explorer, one that has journeyed into the storm's very neighborhood. In July 2016, after a 5-year journey, NASA's Juno spacecraft slipped into orbit around Jupiter. Juno did not take the usual path. Instead of circling the equator, it adopted a unique polar orbit, swinging from pole to pole and diving perilously close to the cloud tops on each pass. This daring trajectory allows Juno to see Jupiter in a way no spacecraft ever has. Its visible light camera, Juno Cam, is a public-powered instrument that has returned the most stunning, intimate portraits of the great red spot ever captured. The images are breathtaking. You can see the intricate textures of the storm, the swirling filaments of cloud at its edge, the chaotic darkness of its central core. It looks less like a smooth oval and more like a colossal, boiling cauldron of crimson gas. But Juno's true power lies in its ability to see what our eyes cannot. The spacecraft is equipped with a suite of microwave radiometers. Think of these not as cameras, but as thermometers that can peer deep below the visible cloud layers. As Juno passes over the spot, these instruments detect the heat, the microwave radiation leaking up from within. Different wavelengths penetrate to different depths, allowing scientists to build a thermal profile, a temperature map that extends hundreds of kilometers down into the storm. This data is revolutionary. For the first time, we are learning about the storm's three-dimensional structure. We now know the Great Red Spot is not a shallow surface feature. It is profoundly deep. Early findings suggest its roots may plunge 200 miles or more into the planet's atmosphere, far deeper than anyone suspected. This means the storm is a massive column of churning gas, a towering skyscraper of a vortex whose foundations are anchored in Jupiter's hot, hidden interior. By combining Hubble's long-term visual records with Juno's deep thermal scans, astronomers are assembling a complete diagnostic picture. It is the difference between a doctor looking at a rash and one who can also order an X-ray and an MRI. We see the surface symptoms with Hubble, and with Juno, we probe the internal anatomy. This combined view is transforming a centuries-old mystery into a solvable puzzle, giving us the tools to ask not just what is happening to the Great Red Spot, but why. Juno's microwave scans have revealed a storm of staggering depth. The data paints a clear picture. The Great Red Spot is not a surface scar. It is a colossal pillar of churning atmosphere, with roots plunging between 300 and 500 kilometers, or roughly 200 to 300 miles, down into the planet's murky interior. That is deeper than the distance from New York City to Washington, D.C., a vertical structure that redefines our understanding of the vortex. Before Juno, many models assumed the storm was perhaps 100 kilometers deep, a powerful but relatively shallow weather system. This new measurement reveals something far more monumental, a storm that is profoundly anchored in the warm, hidden layers of Jupiter itself. This incredible depth helps explain its stubborn persistence. A shallow vortex would be far more vulnerable to disruption from the surrounding jet streams and other storms, easily torn apart by the chaotic winds. But a storm that extends hundreds of miles downward has immense inertia, a deep foundation that resists being shoved around or dismantled. It is the atmospheric equivalent of a towering redwood tree with roots that grip the bedrock, standing firm while shallower shrubs are blown away in a gale. This deep anchoring is likely a primary reason the Great Red Spot has endured for centuries, even as its visible top layer shrinks and changes shape. The horizontal contraction we see from Earth might be just that, a change at the surface, while the deep engine below continues to churn. Juno's instruments did more than just measure depth, they took the storm's temperature. The microwave radiometers detected distinct thermal signatures at different levels. The data shows that the core of the Great Red Spot is warmer at its base, deep down, and grows progressively cooler as you move upward toward the cloud tops we see. This temperature gradient is the engine's fuel line. That warmth at the bottom is the internal heat of Jupiter, the primordial energy from the planet's formation. The storm acts as a chimney, channeling that warm gas upward. As the gas rises and expands in the lower pressures of the upper atmosphere, it cools, forming the dense, bright clouds that define the spot's visible appearance. This continuous cycle, warm gas rising, cooling, and then likely sinking along the storm's edges, is what sustains the vortex against the dissipating forces around it. The composition gradients Juno detected add another layer to the story. The storm's interior shows distinct variations in the concentration of gases like ammonia, which acts as a tracer for vertical motion. These chemical maps confirm the intense upwelling and mixing, showing how the spot dredges material from the abyss. So, while the storm's visible face is narrowing, its deep, warm roots may remain largely intact, a hidden reservoir of stability. This creates a fascinating paradox. The most iconic feature of Jupiter is shrinking before our eyes, yet the new data suggests its heart, beating deep within the planet, might still be strong. The giant may be changing its shape, but it is not yet out of energy. But what does death even mean for a storm? On Earth, a hurricane dies when it moves over land or cold water, its energy source severed. Its winds fade, its clouds scatter, and it ceases to be a coherent, organized system. For a vortex on a planet with no solid surface, the definition is far murkier. The Great Red Spot may never truly vanish in the way a cloud dissipates. Instead, we must consider its potential transformations. One possibility is a kind of metamorphosis. The shrinking, rounding vortex we see today might eventually stabilize at a much smaller size, becoming a new, permanent feature, a junior red spot, if you will. It would lose its title as the solar system's greatest storm, but it could persist for centuries more as a compact, intense cyclone. Another path is dissolution. The erosive forces of the jet streams and chaotic mergers could continue to strip it away until its rotational energy is completely overcome. At that point, the vortex would lose its coherence. Its remaining gases would simply blend back into the turbulent flow of Jupiter's southern hemisphere, its distinctive color fading to nothing. Its death would not be a sudden stop, but a slow unraveling, its energy redistributed to fuel other, smaller storms across the planet. This raises a profound historical question. Has this happened before? Our continuous records only go back 2 centuries, but the storm's own life may span 3.5. In that vast stretch of time, could it have shrunk and regrown, faded and reignited? The century-long gap in observations between Cassini's era and the 1830s is tantalizing. Perhaps the spot we rediscovered was a rejuvenated version of the earlier storm, or a completely new vortex that formed in the same turbulent region. The current shrinkage could be part of a natural, long-term cycle we have simply never witnessed. Yet, the data from our modern, precise instruments tells a compelling counterstory. The rate of contraction observed since the late 19th century, especially the accelerated rounding and flaking events seen by Hubble, appears unique in our detailed records. We are measuring changes in real time that earlier astronomers could only guess at, so we are left with a cosmic riddle. Are we, by sheer luck, present for the final act of a 400-year performance? Or are we merely watching a familiar scene in a much longer play, one where the giant briefly retreats before gathering strength for a future resurgence? The answer lies not just in the storm's past, but in the hidden rhythms of Jupiter itself, rhythms we are only now beginning to hear. The Great Red Spot's fate is woven into the very fabric of Jupiter's face. This colossal vortex is not a solitary island, but a dominant force within a complex atmospheric web, its influence stretching across thousands of miles. To understand the full consequence of its shrinkage, we must look beyond the storm itself to the iconic bands that stripe the planet, particularly the dark south equatorial belt that flows directly alongside it. Jupiter's weather is a system of powerful, alternating jet streams. Think of these as planetary scale conveyor belts of wind, some racing east, others west. The cloudy bands we see are the visual manifestation of these currents. The lighter zones are where gases are rising, cooling, and forming bright ammonia ice clouds. The darker belts, like the South Equatorial Belt, are regions where those clouds sink, warming and clearing to reveal deeper, darker-hued chemicals. The Great Red Spot sits directly between 2 of these ferocious rivers of wind. For centuries, it has acted as a massive atmospheric boulder, permanently disrupting the flow. It deflects the jet streams around its flanks, creating turbulent wakes and influencing the very stability of the belts themselves. The storm's powerful circulation dredges up material from below, some of which gets injected into the neighboring South Equatorial Belt, potentially darkening its color or altering its chemistry. So what happens when that boulder shrinks and changes shape? The entire local weather pattern must adjust. A smaller, rounder vortex presents a different obstacle to the wind. The deflection patterns change, which could alter cloud formation downstream, potentially leading to a visible fading or restructuring of the belt. This is not just theory, we have witnessed it. There are famous episodes in Jupiter's observed history, like the great fading of the South Equatorial Belt, where that entire dark band virtually disappeared for a time, becoming almost indistinguishable from the brighter zones. While the exact causes are complex, many planetary scientists suspect these dramatic events are tied to cyclical outbursts of activity, possibly plumes rising from deep within the planet that interact with and are modulated by the presence of the Great Red Spot. As the storm weakens, its ability to regulate or trigger these planet-wide events may be diminishing. In this way, the spot is far more than a spectacle. It is a crucial control knob in Jupiter's global climate. By monitoring its health, we gain a diagnostic tool for the entire weather machine. Its changing size and color give us indirect readings on the strength of the jet streams, the depth of convective activity, and the stability of the belts. A global map of Jupiter reveals this interconnectedness vividly. You can trace how the jet streams, represented as flowing arrows, are bent and contorted around the stubborn red oval. You can see how its influence ripples outward, affecting cloud formation in distant regions. The slow transformation of the Great Red Spot is therefore a planet-wide experiment in real time. We are watching to see if, as this ancient storm fades, the familiar face of Jupiter begins to change in subtle but profound ways. Will the south equatorial belt become more volatile? Will the storm's absence allow for new, permanent features to emerge? The answers are written in the clouds, and we are only just learning how to read them. The silent transformation of Jupiter's Great Red Spot is a lesson written across our cosmic backyard, one that echoes far beyond the orbit of the giant planet itself. This fading storm is more than a local event. It is a masterclass in the physics of alien skies. Astronomers now know our galaxy is filled with worlds unlike anything in our inner solar system, a menagerie of gas giants that orbit blisteringly close to their stars. These are the hot Jupiters, and they are the most common type of exoplanet we have found. We will never send a probe to those distant fires, but we have a perfect, swirling model right here at home. By deciphering the life cycle of Jupiter's great storm, we are learning to read the faint signals from storms on worlds 1,000 light-years away. Think of Jupiter as the ultimate training ground, a nearby laboratory where we can test our theories of extreme planetary weather. The physics governing the Great Red Spot, the turbulent fluid dynamics of a hydrogen and helium atmosphere under rapid rotation and intense internal heat, are the same fundamental laws that would govern a storm on a hot Jupiter. The difference is one of degree, not kind. A hot Jupiter might be seared by its stars, spinning even faster, its internal heat unimaginably greater, but the core principles of vortex formation, energy transfer, and atmospheric stability remain. When our telescopes, like the James Webb Space Telescope, stare at a distant exoplanet, they do not see a picture. They capture a spectrum, a barcode of light that reveals the composition and temperature of that world's atmosphere. Sometimes that data shows strange, periodic dips and variations. One compelling explanation for these flickers is the presence of giant, persistent storm systems like the Great Red Spot rotating in and out of view. Without understanding how such a storm behaves, lives, and dies on Jupiter, we would have no way to interpret that cryptic stellar signal. The shrinking of our local giant directly informs what a shrinking storm signature might look like in data from another star. This connection turns every observation of Jupiter into a practical exercise for exoplanet science. The detailed measurements from Juno, revealing the storm's incredible depth and thermal structure, feed directly into complex computer simulations. Scientists can take those validated models, scale up the heat, increase the rotational speed, and project them onto the canvas of an alien world. Artist concepts bring these inferences to life, visualizing exoplanets as swirling marbles of color, with massive, dark storm spots dominating their faces. These are not mere speculation, they are illustrations based on physics refined in our own solar system. The Great Red Spot teaches us what is possible. It shows that a storm can persist for centuries, even as it changes. It demonstrates how deep these atmospheric features can root themselves. It reveals the complex interplay between a vortex and the global wind patterns that both feed and erode it. Every flaking event observed by Hubble, every temperature map from Juno, adds a new variable to the cosmic equation. So, while we watch this ancient marvel slowly transform, we are simultaneously learning to see the universe more clearly. The fate of the Great Red Spot is not an isolated curiosity. It is a key piece of a much larger puzzle. The processes that sustain it and the forces that now challenge it are universal scripts being acted out on countless stages across the galaxy. By studying the detailed meteorology of Jupiter, we are essentially calibrating our instruments for the rest of the cosmos. The giant's slow fade is teaching us what to look for and how to understand what we find when we gaze at the faint, twinkling light of a world impossibly far away. The storm is a bridge connecting the familiar dynamics of our neighborhood to the enigmatic whispers of distant suns. This grand cosmic detective story does not belong to professionals alone. The mystery of the shrinking Great Red Spot is being solved in backyards and home observatories around the world. While spacecraft like Juno provide breathtaking close-ups and Hubble delivers its annual checkup, there is a critical gap in our data, the long stretches of time between those professional observations. This is where a global network of dedicated amateur astronomers steps in, their personal telescopes trained on Jupiter night after night, providing the essential continuous watch. With modern, affordable equipment, an enthusiast can capture images that rival those from major observatories just a few decades ago. They track the subtle shifts in the spot's color, its precise position relative to the cloud bands, and any sudden flaking events. When a professional telescope cannot be pointed at Jupiter, these citizen scientists are there, logging changes and sounding the alarm if something dramatic occurs. Their collective logbooks form a priceless, real-time record of the giant's health, a human-powered early warning system for planetary change. The data they contribute is not just supplemental, it is foundational, filling the timeline with details that would otherwise be lost to the night. This collaboration has been supercharged by the digital age, most spectacularly through a spacecraft's camera that belongs to everyone. When the Juno mission launched, its visible light camera, Juno Cam, was described as a public engagement instrument. The team invited the world to participate. They post the raw, unprocessed image data online, and anyone can download it. The public votes on which features of Jupiter the camera should target on upcoming orbits. Then, a global community of image processing enthusiasts using software on their home computers transforms those stark black and white data files into the breathtaking, full-color portraits that circulate across the news and social media. These are not official NASA releases, they are stunning works of art and science created by teachers, students, graphic designers, and retirees. Their processed images reveal details and textures that might otherwise be overlooked, their different techniques highlighting various aspects of the storms and cloud structures. This has led to genuine discoveries as keen-eyed amateurs spot small vortices, unusual color changes, or intricate wave patterns in the atmosphere that warrant further scientific study. The Juno Cam Gallery is a testament to what happens when you open a window to another world and hand the camera to humanity. The result is a living, breathing album of Jupiter's transformation. You can scroll through forums and websites and see a mosaic of the Great Red Spot from 100 different eyes. There is the meticulously sharpened image from an amateur in Chile, showing the intricate filamentary structure of the storm's outer rim. Next to it, a vibrant, contrast-enhanced view from an enthusiast in Japan highlights the stark difference between the deep red core and the surrounding pale haze. Another image, processed to bring out subtle color gradients, reveals a faint tendril of material being drawn away from the main vortex, a possible flaking event caught in the act. These are not just pretty pictures, they are data points. When an amateur captures a sudden change, the global network shares it instantly, alerting professionals to turn their larger instruments toward Jupiter for a closer look. This synergy creates a continuous monitoring web that no single agency could ever fund or maintain. It means the Great Red Spot is never truly out of sight. It's every shiver and sigh noted by someone somewhere under a dark sky. The storm's slow fade is thus documented by a planet-wide community, a shared vigil for a shared wonder. This collective gaze turns a distant astronomical event into a personal experience, connecting individuals directly to the dynamic face of a giant. The question of what comes next for the spot is not just for scientists in labs, it is for anyone who has ever looked up at the night sky and felt a spark of curiosity. The next clue in this centuries-old mystery might well come from your neighbor's rooftop telescope. Jupiter's crimson vortex is not the only giant to have stalked the solar system. To truly appreciate its endurance, we must place it within a wider gallery of alien tempests, each a unique expression of its home world's chaotic heart. Consider Neptune, that distant, icy blue giant. When Voyager 2 raced past in 1989, it revealed a stunning surprise, a colossal dark blue storm in the southern hemisphere, aptly named the Great Dark Spot. It was comparable in size to Earth, with winds screaming at over 1,200 miles per hour, the fastest ever recorded in the solar system. Yet, when the Hubble Space Telescope turned its gaze to Neptune just a few years later, the spot was gone. It had simply vanished, leaving astronomers to wonder if it had dissipated or been covered by other atmospheric activity. Neptune's storm was a spectacular but fleeting phantom, a reminder that some planetary giants can flicker in and out of existence within a human lifetime. This transient nature stands in stark contrast to the stubborn persistence of Jupiter's Great Red Spot. Why the difference? The answer lies in the engines that drive them. Neptune, unlike Jupiter, lacks a significant internal heat source. Its furious winds are thought to be powered by the delicate balance of the faint warmth it receives from the distant sun and the release of gravitational energy as heavier material sinks toward its core. This creates a more shallow, turbulent, and ultimately less stable atmospheric system, where massive storms can form with drama but lack the deep, rooted energy to sustain themselves for centuries. Then there is Saturn's North Pole, home to one of the solar system's most bizarre and geometric weather patterns. Here, a six-sided hexagon of clouds wider than two Earths spins with a clockwork precision. This is not a storm in the traditional sense, but a persistent, stable jet stream pattern, a standing wave etched into the atmosphere. Winds race along its 6,000-kilometer-long walls at speeds comparable to a terrestrial hurricane, yet the hexagonal structure itself has remained locked in place for decades, possibly centuries. It is a phenomenon born from the unique fluid dynamics of a rapidly spinning gas giant, a demonstration of how orderly shapes can emerge from chaos. While the Great Red Spot is a deep, rotating column, Saturn's hexagon is more like a shallow, atmospheric tattoo, a pattern painted onto the cloud tops by the planet's internal rhythms. It shows that longevity in planetary weather can take many forms, from a churning vortex to a rigid geometric wave. All of these alien systems operate under a completely different set of rules than the storms we know on Earth. Our hurricanes are powered by solar heat evaporating warm ocean water. They are essentially heat engines that run on water vapor, and they die a quick death when they move over land or cold water, their fuel supply cut off. They are surface skimmers, rarely extending more than 10 miles deep into our comparatively thin atmosphere. On a gas giant, there is no land, no ocean to cross. The atmosphere itself is the ocean, extending thousands of miles down into an abyss of progressively denser, hotter fluid. Storms like the Great Red Spot are not driven by sunlight on water, but by the planet's own internal furnace and its dizzying rotation. They are not surface features, but deep-seated structures, colossal columns of circulating fluid that tap into the planet's primordial energy. This fundamental difference in physics is why a storm on Jupiter can outlive civilizations while a hurricane on Earth is measured in days or weeks. A simple comparative graphic makes this astonishing scale clear. It would show Earth's largest hurricane as a tiny speck next to the sprawling oval of the Great Red Spot, with Neptune's vanished dark spot and Saturn's hexagonal wave providing other points of alien reference. The numbers tell the story: wind speeds measured in hundreds of miles per hour on Earth, but in the thousands on the outer planets, durations measured in days versus centuries, and depths measured in miles versus hundreds of miles. This comparison frames our local giant not as an oddity, but as the ultimate example of a class of storm that can only exist in the deep, fluid atmospheres of gas giants. Its slow fade is not just about one vortex dying. It is a rare chance to observe the life cycle of a type of meteorological beast that we now know fills the galaxy, a beast whose final breaths we are uniquely positioned to witness. The question is a natural one, but the answer reveals a profound difference between worlds. When we see a planet's most famous feature shrinking, our minds leap to a familiar culprit: climate change. Yet, applying Earth's framework to Jupiter is like trying to use the rules of a pond to understand the ocean. Earth's climate is a delicate and complex dance between the sun, our atmosphere, the vast oceans, and the living biosphere. The carbon dioxide released by burning fossil fuels acts as a blanket, trapping more of the sun's heat and disrupting that global balance. Our climate change is at its heart, a story of chemistry and solar energy absorbed at the surface. Jupiter has no oceans to warm, no forests to burn, no industries emitting greenhouse gases. Its atmosphere is a seething cauldron of hydrogen and helium, with traces of methane, ammonia, and water vapor, but it lacks the intricate feedback loops that define a terrestrial biosphere. The primary driver of Jupiter's weather is not the faint sunlight it receives, but the fierce heat radiating from its own interior. So, if we are asking whether human activity is causing the Great Red Spot to shrink, the answer is a definitive no. The forces at work are entirely internal to the Jovian system, a product of its own immense and ancient energy. However, the word climate itself has a broader meaning in planetary science. It is not limited to Earth-like conditions. A planet's climate is simply the long-term state of its atmosphere, the average of its chaotic weather over centuries or millennia. In that sense, Jupiter absolutely has a climate, and it is undergoing change. The shrinking of the Great Red Spot may be one visible symptom of a much slower, planetary-scale shift in how Jupiter distributes its internal heat. Think of it this way: Earth's current climate change happens on a scale of decades, a rapid spike on our geological timeline. Jupiter's climate cycles likely operate on scales of thousands or even millions of years. Our entire recorded history of the storm is less than a blink in the life of the planet. We have only been watching with precise instruments for a few decades, a snapshot that might capture a mere moment of a vast, slow oscillation. We do not know if the spot's shrinkage is a permanent decline or merely a contraction phase in a million-year cycle of growth and decay. We are like a person who walks into a movie theater for the first time, sees a single dramatic scene, and must guess the entire plot. We have no idea what came before or what comes next. This distinction is crucial for how we search for life and understand our place in the cosmos. When we study exoplanets, we are intensely interested in their climate stability. A world with wild, unpredictable temperature swings or vanishing atmospheres is a poor candidate for life as we know it. Earth's climate, for all its current fragility, has been remarkably stable for billions of years, allowing life to take root and evolve. Jupiter's climate is one of constant, magnificent violence, a perpetual storm where stability is found not in calm, but in the enduring patterns of chaos. The Great Red Spot, even as it fades, is a testament to that kind of stability. It represents a persistent order emerging from the tumult, a landmark that has weathered the planet's own deep rhythms for centuries. So, while Jupiter is not experiencing Earth-style climate change, its atmosphere is far from static. It is a fluid, dynamic, and aging giant, and the transformation of its greatest storm is a message. It tells us that all planets, whether rocky worlds with thin skins of air or gas giants with atmospheres thousands of miles deep, have lives and histories written in the slow, grand language of physics. We are just beginning to learn how to read it. So where does the data point? To peer into the storm's future, we must turn to digital crystal balls, the supercomputer simulations that attempt to recreate Jupiter's alien physics. Teams of researchers feed every scrap of data from Hubble and Juno into these colossal models, programming the fundamental laws of fluid dynamics onto a virtual gas giant. They must account for the planet's rapid rotation, its deep internal heat, the complex chemistry of its clouds, and the chaotic interplay of countless smaller storms. It is one of the most computationally demanding tasks in all of planetary science, requiring months of processing time on some of the world's most powerful machines just to simulate a few Jovian years. The results are not a single prediction, but a spectrum of possibilities, each hinging on subtle assumptions about the forces we cannot yet fully measure. Some of the most detailed simulations produce a future that feels familiar. They show the Great Red Spot continuing its current trend, slowly shrinking and becoming more circular. In these models, the vortex reaches a new equilibrium, a compact and intense storm perhaps half its current width. This junior red spot could then persist for many more centuries, a smaller but still permanent landmark on the face of Jupiter. The simulations visualize this as a tightening knot of crimson energy, holding its own against the buffeting winds, a diminished but unbroken legacy. Other model runs tell a more dramatic story. They tweak the parameters, perhaps increasing the shear force of the surrounding jet streams or reducing the upwelling of heat from below. In these scenarios, the erosion we see today accelerates. The storm's outer layers are stripped away in larger, more frequent flaking events. The vortex loses its coherent rotation, beginning to wobble and fray at the edges. The final act in these simulations is not a stable smaller spot, but a dissolution. The remaining cloud structure stretches into a long, faint ribbon before being completely shredded and absorbed by the chaotic flow. The visualizations for this path are haunting, showing the iconic oval dissolving like a drop of red dye in a turbulent stream, its color bleeding away until only the bland tan of Jupiter's background clouds remain. The challenge and the reason for such divergent forecasts lies in the sheer complexity of the system. Modeling the Great Red Spot is not like forecasting a hurricane on Earth, where we have centuries of weather data and can directly measure the ocean temperatures that fuel it. We are trying to simulate a storm whose roots plunge into an abyss we cannot see, driven by heat flows we can only infer. The models must make educated guesses about the viscosity of Jupiter's deep atmosphere, the exact profile of the jet streams hundreds of miles down, and the stability of the storm's deep thermal column. A tiny change in any one of these unknown variables can steer the virtual storm toward a completely different fate. This is why the predictions carry large, honest uncertainties. The supercomputer visualizations themselves are crucial tools. They transform columns of numbers into swirling, dynamic portraits of potential futures. Scientists can watch as their digital storm contracts, watch as tendrils of red gas are sheared away by violet jet streams, observe how a merger with a smaller white oval sends violent ripples through the vortex's core. These are not mere animations, they are numerical experiments. By comparing these simulated evolutions against the real, observed changes from Hubble, researchers can test which of their assumptions are correct. If the real spot behaves more like the simulation where the jet streams are strengthening, that path gains credibility. If it holds its size during a period the model predicted it would shrink, they know to go back and adjust the code. It is a slow, iterative process of aligning the digital twin with its fading celestial counterpart. So while we cannot say with certainty whether the Great Red Spot will vanish in 50 years or 500, these models give us the framework to understand the mechanisms at play. They tell us what to watch for. They instruct our telescopes to monitor the specific jet streams flanking the storm for signs of strengthening. They tell Juno's scientists which deeper thermal signatures might hint at a failing engine. Each new observation from the real Jupiter is a clue that helps us refine the simulation, bringing the blurry image of tomorrow into slightly sharper focus. The future of the oldest storm we know is being written in a language of mathematics and fluid dynamics, translated by light from across the solar system, and rendered possible by the quiet hum of supercomputers right here on Earth. The disappearance of that crimson eye would leave a permanent blind spot in our shared view of the cosmos. For generations, the Great Red Spot has been more than a scientific curiosity, it is a cultural icon. It is the first feature anyone sketches when drawing Jupiter, the defining mark that makes the gas giant instantly recognizable in a lineup of planets. Its absence would fundamentally alter the face of our solar system in textbooks, posters, and planetarium shows. Jupiter would no longer be the planet with the Great Red Storm. It would become a world of bands and zones, its personality subtly but irrevocably changed. The public imagination, which has for so long associated that swirling oval with the very concept of an alien world, would have to adjust to a new normal, a solar system where one of its most famous landmarks had simply faded away. This would be a profound loss of a celestial touchstone, a piece of our cosmic identity quietly retired. For scientists, however, such an event would be the opportunity of a lifetime. The death of a giant storm is a process we have never witnessed in detail. Observing the Great Red Spot's final unraveling would provide an unparalleled masterclass in atmospheric decay. Every flake of cloud torn away, every shudder in its rotation, every change in its thermal signature would be a data point in the ultimate experiment on vortex stability. How does a centuries-old, deeply rooted weather system finally surrender its energy? Does it dissipate evenly, or does it fragment into smaller, short-lived vortices? The answers would refine our models of fluid dynamics not just for Jupiter, but for every turbulent atmosphere in the universe. This would be the rare chance to watch a fundamental planetary process from beginning to end, to see the final chapter of a story we have only ever read in fragments. The storm's vanishing act might also be a signal, a surface symptom of a much deeper planetary shift. If the Great Red Spot is indeed a chimney for Jupiter's internal heat, its collapse could indicate that the deep convective plume feeding it has finally weakened or shifted course. This could herald a reorganization of the planet's global circulation patterns. The jet streams that have flowed around the storm for centuries might realign. The famous South Equatorial Belt might change its color or intensity permanently. We could be witnessing the start of a new climatic era for Jupiter, one defined by the absence of its once dominant storm. The planet's weather machine would operate without its largest cog, and the resulting changes would teach us how interconnected and sensitive these giant systems truly are. This is why astronomers are not just watching, they are preparing. The potential end of the Great Red Spot has mobilized a global observation campaign unlike any other for a planetary feature. Every major telescope, from Hubble to the James Webb Space Telescope and powerful ground-based observatories, has scheduled regular monitoring sessions. Their goal is to capture every possible wavelength of light, from the visible to the infrared, building a multidimensional movie of the storm's demise. The Juno mission, though its primary mission is complete, continues its extended operations with the spot's health as a key science objective. Its microwave radiometers poised to detect any failure in the storm's deep thermal engine. Amateur astronomers worldwide are on high alert, their continuous watch more critical than ever to fill the gaps between professional observations. Data archives are being prepared, protocols established, and models updated in real time, all to ensure that if the giant takes its final breath, we will have a complete record of its last gasp. The goal is to leave nothing to speculation, to document the death of a wonder with such precision that its final moments become a permanent gift to science, a legacy of data that will inform our understanding of alien skies for centuries to come. The deep red color of the storm remains an active chemical puzzle. We know it likely involves compounds like sulfur or phosphorus, but the exact recipe and the specific chemical pathways that create that rusted hue are still being decoded. Is the color a sign of the storm's health or merely a byproduct of its depth? Each new observation from Hubble and Juno adds another piece to this cosmic chromatogram, yet the full picture eludes us. This leads directly to the grandest uncertainty of all. Is the shrinkage we are measuring the beginning of the end, or just another chapter in a million-year story of expansion and contraction? Our records are simply too short to know if this is a terminal decline or a routine phase. Without a longer timeline, we are like a doctor who has met a patient only once and must diagnose their lifelong health from a single snapshot. The stunning data from Juno confirmed the storm's roots plunge hundreds of miles down, but what lies at the very base of this atmospheric skyscraper? Does it connect to a stable, convective plume rising from the metallic hydrogen layer, or does it tap into a more chaotic and shifting energy source? We have mapped the chimney, but we still cannot see the fire, and perhaps the most complex question involves the storm's energy budget. Precisely how much internal heat flows into the vortex, how much kinetic energy is contained in its spin, and how much is being lost to the eroding jet streams. Quantifying this balance is essential to predicting its future, yet it requires measurements of the deep atmosphere we still cannot fully make. These are not minor gaps, they are fundamental mysteries about how giant planets live and breathe. To solve them, the watchful eyes never blink. The Hubble Space Telescope continues its annual planetary health check, building that critical long-term record. The Juno spacecraft, in its extended mission, makes ever more daring passes, its microwave instruments probing deeper and its camera capturing finer details of the erosion at the storm's fraying edges. Every byte of data it beams back is scrutinized by teams around the world, fed into those supercomputer models to refine our virtual Jupiter, and the future holds even greater promise. The European Space Agency's Jupiter Icy Moons Explorer, called JUICE, is now on its long journey. While its primary target is the potentially habitable moons like Ganymede, its powerful suite of instruments will also turn a keen eye on Jupiter's atmosphere itself. It will offer a new, complementary perspective, studying the gas giant's complex magnetic environment and its interplay with the weather below. Together, these missions form a relay of discovery, passing the baton of observation from one generation of explorers to the next, ensuring that even as the giant storm changes, our understanding continues to grow. The equations swirling within a simulation of Jupiter's storm might one day help design a quieter, more efficient jet engine. This is the hidden legacy of studying the Great Red Spot, a cascade of benefits that begins in the clouds of a gas giant and ends in the tangible improvements of our own world. To predict the fate of that ancient vortex, scientists must first solve one of physics' most notorious problems, the mathematics of turbulence. Turbulence is the chaotic, swirling motion that appears when a fluid, whether air, water, or hydrogen gas, flows past an obstacle or at high speed. It is the reason a river churns around a rock, why a plane shakes in a storm, and what gives the Great Red Spot its intricate, filamentary edges. For centuries, describing turbulence with precise equations has been a monumental challenge. The great physicist Werner Heisenberg once reportedly said he would have two questions for God: why relativity and why turbulence, and he was confident God would have an answer for the first. The joke underscores a deep truth: Turbulence is fiendishly complex because it operates across scales, from the massive swirl of the storm down to the tiniest eddies within it, all interacting in a chaotic dance. To model the Great Red Spot, supercomputers must simulate this multi-scale chaos in a rotating, heated, bottomless fluid, a task that pushes processing power to its absolute limits. The code written for these simulations is a masterpiece of computational fluid dynamics, algorithms designed to capture the birth, life, and decay of vortices in an environment utterly alien to Earth. But the principles are universal. The same core physics that governs the shearing of a red cloud filament on Jupiter governs the airflow over an airplane wing or the mixing of fuel in a combustion chamber. By striving to simulate the largest storm in the solar system, researchers are honing tools that can model turbulence with unprecedented accuracy. These refined models are already finding their way into earthly laboratories. Aerospace engineers use them to design next-generation aircraft with smoother aerodynamics, reducing drag and fuel consumption. Automotive companies apply them to create more efficient engine designs that minimize turbulent energy loss. Even the quest for clean energy benefits as physicists use similar models to predict the behavior of superheated plasma in experimental fusion reactors, where containing a turbulent star-like energy is the key to success. Perhaps the most direct application is in our own weather forecasts. While Earth's atmosphere is thin and shallow compared to Jupiter's, it is still a turbulent fluid. The advanced data assimilation techniques and high-resolution modeling developed to track a storm that lasts centuries are improving our ability to predict hurricanes that last weeks. The supercomputers that run global climate models share a direct lineage with those visualizing Jupiter's jet streams. Visualizing this connection is powerful. Imagine a split screen. On one side, the swirling crimson and cream of a supercomputer simulation of the Great Red Spot, its edges fraying into digital filaments. On the other, that same underlying code is shown generating a simulation of air flowing through a jet turbine, the currents optimized for maximum efficiency. Another graphic might show the turbulent flow around a car rendered in the same visual style as the Jovian storm, a direct link from cosmic chaos to human engineering. This framing transforms the Great Red Spot from a distant object of study into a grand challenge, a natural laboratory that forces us to sharpen our most fundamental tools for understanding the physical world. Each observation, each new data point from Juno is a test for our mathematics. Each refinement to the simulation is a step toward not just predicting the storm's future, but toward building a better, more efficient future here at home. The giant slow fade is, in a very real sense, teaching us how to master the hidden flows that shape our own world. One persistent myth paints the Great Red Spot as a gaping hole, a window down into Jupiter's fiery depths. This is a compelling image, but it is scientifically wrong. The spot is not an absence, it is a colossal presence. It is not a hole, but a mountain of clouds. Data from spacecraft like Juno confirms it is a towering, high-pressure anticyclone, meaning the air within it is actually rising. Think of it as a colossal atmospheric upwelling, where gases are forced upward from the deep, warm layers, expanding and cooling to form the dense, crimson cloud tops we see. It is a solid, physical structure, a skyscraper of swirling gas whose roots plunge hundreds of miles down. A simple side-by-side graphic makes this undeniable. On one side, an artistic misconception shows Jupiter with a literal hole punched through its clouds, revealing a glow beneath. On the other, a cutaway scientific illustration reveals the truth, a deep, red column rooted in the planet's hot interior, standing proud above the surrounding cloud decks. The spot is a peak, not a pit. Another common leap in logic ties the storm's shrinking to its imminent and total disappearance, while the contraction is real and measured, declaring its death date is premature. Planetary atmospheres operate on timescales that dwarf human lifetimes. The spot has likely undergone periods of growth and decay before, across centuries we never recorded. The current shrinkage could very well be a phase, not a finale. Many sophisticated computer models suggest the vortex may reach a new, smaller equilibrium, a compact and intense storm that persists for a long time to come. It might lose its title as the solar system's largest, but it could remain a permanent, albeit diminished, feature on Jupiter's face. The key is to separate the observed trend from a guaranteed outcome. We are watching one scene in a very long movie, and we do not have the script. Sensational headlines sometimes scream that the Great Red Spot is exploding or that its changes will wreck Jupiter's climate. These claims misunderstand the scale and nature of the planet. The flaking events where red material shears off are a form of erosion, not an explosion. They are a slow, graceful unraveling at the edges, not a violent detonation. As for catastrophic planetary change, Jupiter's atmosphere is the definition of stable chaos. It is a system of unimaginable energy and violence that has maintained its banded structure for billions of years. The Great Red Spot, for all its grandeur, is one feature within that vast, turbulent engine. Its transformation, while significant to us, is a local event for Jupiter. The planet's global wind patterns, its heat flow, its fundamental chemistry, these are driven by forces far more powerful and deep-seated than any single storm. Losing the spot would be like the Atlantic Ocean losing a particularly famous and long-lived whirlpool. The ocean itself would hardly notice, even as mapmakers mourn the loss. Clearing these myths is not just about accuracy, it is about appreciating the storm for what it truly is and what its changes truly mean. It is a dynamic, physical phenomenon obeying the laws of fluid dynamics, not a mysterious portal or a pending apocalypse. By correcting these misconceptions with clear visuals and straightforward explanations, we ground a cosmic wonder in the reality of science, which is often more astonishing than any fiction. The truth is, the gradual fading of this giant is fascinating enough without exaggeration. It presents a genuine, slow-motion mystery about the longevity of order within chaos, a puzzle we are uniquely positioned to solve with our telescopes and probes. The storm's real story is one of resilience, change, and deep planetary connection, a narrative written in the slow language of physics across the face of a world that makes our own look like a tranquil haven. The story of this shrinking giant is not locked away in data files. It is written across the night sky for anyone to read. With a modest investment and a little patience, you can witness Jupiter's changing face with your own eyes. A backyard telescope with a primary mirror or lens at least 4 inches across is your passport to this view. On a clear, steady night, point it toward the brightest star in that part of the sky, and you will be greeted by a sight that has captivated humans for generations. There will be the creamy disk of Jupiter, striped with its dark and light bands and flanked by its 4 largest moons like tiny diamonds on a string. And if the timing is right and the atmospheric seeing is calm, you will spot it. A pale, salmon-pink oval nestled in the southern hemisphere, often nestled just below the dark south equatorial belt. It will not look like the vibrant, high-contrast images from spacecraft, but as a subtle, distinct smudge of color, a ghost of the Titan it once was. That moment of recognition, when you locate that faint, ancient storm in your own eyepiece, connects you directly to the centuries of observers who came before, all documenting the same enigmatic feature. To catch the Great Red Spot during its window of visibility, you will need to know when Jupiter's rapid rotation brings it around to face Earth. The planet spins once every 9 hours and 56 minutes, so the spot is in view for a few hours at a time, but its position changes nightly. This is where modern technology becomes your guide. Free astronomy apps and websites allow you to input your location and will tell you the exact times, down to the minute, when the Great Red Spot is centrally placed on Jupiter's disk. You can plan your observing sessions knowing that at, say, 10:47 p.m., you will have a front row seat to the solar system's most famous storm. For those who want to capture their own record of its transformation, the world of amateur astrophotography has been revolutionized. Affordable planetary cameras, which are essentially small, sensitive video sensors, can be attached to your telescope. Instead of taking a single, shaky photograph, you record a video of Jupiter as it drifts across your field of view. Specialized, free software then analyzes that video, selects the sharpest frames from thousands, and stacks them together to create a single, detailed image that cuts through our turbulent atmosphere. The results can be astonishing. Amateurs regularly produce images that reveal the spot's shape, the surrounding cloud details, and even the shadows of the moons cast upon Jupiter's clouds. To see what you can expect, picture a spectrum of views. Through a small telescope, Jupiter is a bright oval with two dark bands. With a 6-inch telescope under good conditions, the Great Red Spot becomes a clear, pale indent on the southern edge of one of those bands. Through a larger 10-inch instrument, more subtle features emerge, like the intricate textures within the spot itself and the delicate structure of the surrounding white zones. Each step up in aperture pulls you closer, making you not just a spectator, but a participant in this long-term vigil. By training your lens or your eye on that pale oval, you join a global network of watchers. You become part of the story, contributing your own observations to the collective understanding of this cosmic wonder's fate. The next clear night could be your chance to see history in the making, to witness the slow fade of a legend from your own backyard. This journey has taken us from a crimson smudge in a telescope to a profound cosmic mystery. We began with the ancient storm itself, a churning giant older than our nations, and followed the clues of its slow, undeniable fade. We became detectives, sifting through theories of atmospheric erosion and chaotic mergers, using the tools of Hubble and the deep vision of Juno to peer into its hidden heart. The story of the Great Red Spot is a powerful reminder that our solar system is not a static museum. It is a dynamic, ever-changing arena where even landmarks we thought were permanent are writing new chapters within a human lifetime. Whether this particular vortex eventually fades to a memory or stabilizes as a smaller sentinel, its study has fundamentally deepened our understanding of fluid worlds. It has taught us that stability on a gas giant is a persistent form of chaos, and that the weather there operates on a scale both vaster and more intimate than we ever dreamed. This knowledge now travels with us, a lens through which we view the swirling atmospheres of distant exoplanets. So the next time you have a chance, look up. Find Jupiter, that brilliant jewel in the night sky, and know that on its face, a centuries-old drama is quietly unfolding. Follow the latest images from Hubble and the ongoing revelations from Juno. Stay curious, because the greatest lesson of the Great Red Spot is that our cosmic neighborhood is alive with stories, and we are just beginning to learn how to read them.